In this video, we will learn about olefinations, which are a type of carbonyl substitution reaction in which the carbonyl oxygen is actually the leaving group. If you haven't heard the word before, olefin refers to basically just alkene. It's another word for alkene. And olefination of carbonyls turns out to be a very important synthetic technique because it's a way to form carbon-carbon bonds, making alkene specifically, which we know can be converted into all sorts of other functional groups. Just to give you a quick relevant example, the molecule here on the left is vitamin A acetate, which hopefully we can understand is something important for world and society. It turns out that when people try to synthesize this, at least initially, looking at this, you see a lot of double bonds in a row. And nature produces a lot of molecules like this, and for the synthetic chemist, one way to make these double bonds is through the olefination of a carbonyl. So I have that broken down retrosynthetically here into what is the nucleophilic piece and then the electrophilic piece. So again, in all of these olefinations, our strategy is to use a carbanion as our nucleophile. That's going to attack the carbonyl, creating a tetrahedral intermediate. And then through some of the chemistry that we'll see, the tetrahedral intermediate actually gets converted into having the oxygen as a leaving group, and that's how overall some sort of elimination takes place to get to the olefin or alkene as the product. The most famous olefination reaction, the Wittig reaction, which we'll talk about momentarily, uses a reactant that's called an ylide, so Y-L-I-D-E. And so before we get to the actual reaction, we should talk about what an ylide is. So by definition, an ylide is a molecule that has two adjacent atoms that both have a full octet and have opposite formal charges. And so here I'm showing you, for example, a phosphonium ylide, because the phosphorus here has 8 electrons around it, full octet. Carbanion here, but still full octet. We can think of this as having a resonance form like so. This would be called the ylene resonance form. It turns out that this is the preferable way to draw the molecule. This is much more accurate to reality. So if you look at, for example, bond lengths in molecules like these, they look much more like a single bond than a double bond. That being said, you'll see a lot of examples out there where they're still written out as an ylene. And so it's just something to be aware of. Whenever you see kind of a phosphorus atom like this that seems to have kind of 10 valence electrons around it, one of them being, or I guess 4 of them being part of double bond to carbon, that's actually going to get you a nucleophilic carbanion. And so if we're ever going to be using ylides, we should also know how to make the ylide. And it turns out that that's not too difficult. What you really do is just take a nucleophile and perform an SN2 reaction on an alkyl halide. That displacement, so here using triphenylphosphine as the nucleophile, then leads to the formation of a tetrasubstituted phosphorus, which is then cationic. And so we first make this phosphonium salt. Usually these are pretty stable species, so you can run this reaction. This will crystallize out nicely as a solid, and you can just keep this in a bottle until you need it. This molecule has a pKa of 22, and so that's pretty typical for phosphoniums. And of course you can imagine that the pKa will either go up or down depending on what this R group out here is. When you're ready to perform the olefination, what you would then do is to deprotonate the phosphonium salt, and that will get you to the ylide. So now let's look at 4 of these olefination reactions. So the first one we'll talk about is the Wittig olefination, often called the Wittig reaction. And in this reaction, we're going to olefinate a carbonyl, and in general, when there is the possibility of forming different stereoisomers as a product, the Z alkene is favored during the Wittig reaction. The other characteristic of a Wittig reaction is that it goes through what's called an oxaphosphatane intermediate, which we'll see in a second. So I'm showing you a nice simple example here. So I have an ethyl triphenylphosphonium salt that I'm going to deprotonate using butyl lithium. So this is a very strong base. And then after I deprotonate it, I don't need to isolate what I've made, which is the ylide, but rather I can then in step 2 kind of go in as a chemist and just add in my electrophile so that the next reaction step can take place. In this case, of course, I'm adding an aldehyde. That gets me to the Z product here. Mechanistically, so we're going to do our first deprotonation. So we'll draw that out here. I'm using butyl lithium as the base, and so just a reminder that this is an organolithium compound. And organolithium compounds have this carbon-lithium bond, which is often shown just as a sigma bond or a covalent bond rather than an ionic one. But that pair of electrons there is still pretty nucleophilic and basic. So we should expect a reaction like so. This gets us to the byproducts of lithium chloride. So lithium plus here, chloride counteranion here, and just butane, which is a gas and kind of flies away from your reaction mixture. Just to remind us, the pKa of butane is around 50, so that's why this is a very favorable acid-base reaction. You're only going to have ylide. There's not an equilibrium here. Once you've given the reaction a little bit of time to form the ylide, then you would go through and add in your electrophile. This electrophile then will do a carbonyl addition reaction, but not so simply. We'll get the addition to the carbon of the carbonyl, but at the same time, that pi bond, rather than getting pushed onto the oxygen, actually simultaneously just comes over nearby because there's a electrophilic phosphorus nearby. So this is kind of a cyclic transition state. So we have 4 atoms, and they will bond together to form this 4-membered ring, which is called the oxaphosphatane. So something important here is that I've started to indicate stereochemistry, and that's because from my selection of reactants here, I can either have the 2 large groups, so in this case the methyl group and the phenyl group here as cis to each other, or I can have them actually be formed trans to each other. So in this reaction, there's this possibility of 2 different reaction pathways getting you to 2 different cyclic oxaphosphatane intermediates. Once these oxaphosphatanes are formed, they generally react pretty quickly and decompose down. And so let me go through the arrow pushing here. The driving force for this reaction is the formation of a very strong phosphorus to oxygen double bond, and that comes out as a byproduct in the middle here, triphenylphosphine oxide. So these arrows could look like so. And you can actually also draw them the other way, which I'll do down here. Because it's a cyclic transition state, it kind of doesn't matter if your arrows go clockwise or counterclockwise. You're always getting to the same end products. In doing so, then we create the pi bond in the alkene, and again that pi bond in the phosphorus-oxygen double bond. These products are formed in a major and minor amount, and so at least in this specific combination of reactants, this comes out to be about a 60% Z, 40% E product mixture. So not the most selective reaction, but some amount of selectivity. As kind of a more practical side note, triphenylphosphine oxide is a terrible byproduct. As soon as it's made, it sticks to literally everything, and it's extremely difficult to get rid of your byproduct triphenylphosphine oxide from your actual product. And so this is actually a huge problem because in the development of a lot of pharmaceuticals, Wittig reactions are used, but this is not something good for us to take and eat a lot of. And so this contaminant can be often bad enough that the entire process of synthesizing a promising drug gets completely derailed because it's just not possible to get something pure enough. Taking a step back, a question that should be lingering is, well, why is the Z-alkene the major product when usually Z-alkenes have a little bit more steric energy, right? Because now we have the 2 larger groups on the same side of the alkene. And that's a good question. It turns out that for all sorts of reasons, the transition state getting to the cis oxaphosphatane intermediate is lower in energy than the transition state to get to the trans oxaphosphatane intermediate. However, this trans intermediate is itself lower in energy. So it's this interesting case where, again, the transition state energy is lower to a higher energy intermediate. And that's not something you would necessarily know ahead of time, but that's just how it is in this situation. So then, of course, if you have a reaction that can olefinate and make Z-alkenes, then we should also have a reaction that can olefinate and make E-alkenes. And if you think back to the Wittig reaction, the problem was that it was faster to form the cis oxaphosphatane intermediate leading to the Z-alkene. And even though the trans oxaphosphatane intermediate was lower in energy, for whatever reason, the transition state energy was a little bit higher. So those lower mechanistic steps I showed you don't happen as often. So then our solution is to figure out a way to get the reaction to equilibrate between intermediates to find the lower energy intermediate. And through a combination of efforts, the Horner, Wadsworth, and Emmons came up with a reaction which is much easier named the HWE reaction. And so what they did is to not use a phosphonium, but rather a phosphonate. So this phosphonate right here introduced enough change to get the reaction to favor the E alkene. So let me walk you through how this looks. So the first step is nothing different. We still have a fairly acidic hydrogen right here, and the deprotonation with a strong base should get you to a carbanion. Notice that in this case this is no longer an ylide, but rather just a phosphonate carbanion, because we only have the carbanion charge here. In the first step, or I guess the next step, we're going to get addition to the carbonyl. So addition like so. However, we do not get the subsequent kind of attack back of the carbonyl oxygen onto the phosphorus. We can rationalize that by noticing that this phosphorus is not positively charged, so it's going to be a little bit less electrophilic. And so what we get is actually an intermediate like so. So this is kind of an open chain rather than a four-membered ring. And this subtle change is enough that the reverse process will also take place, and so we get an equilibrium now between all of these species that eventually will find the bottom intermediate as the more stable intermediate, because if you think about the Newman projections here, you can get these two large groups here to be anti to each other. These open chain intermediates can then eventually cyclize, but that cyclization again happens as a second step to form the four-membered ring intermediate, so like so or like so, thus getting you to here. And at this point you can see the setup to making the E alkene versus the Z alkene, and again the equilibrium will tend to favor the bottom side, or this bottom pathway here, which overall gets us to more of the E alkene product. The elimination to get to the alkene is analogous to that in the Wittig reaction, so the collapsing of the ring. And the byproduct we get is this phosphonate here, and this byproduct is a little bit less annoying because it's very easily dissolved in water, and so we can easily wash it away from our products, assuming our products are not also soluble in water. And so if you're thinking about comparing the Wittig reaction to the HWE reaction, a major difference that we should see is the extent to which this carbanion is stabilized. So you'll notice in the HWE reaction I have this ester on the other side, and that's kind of a requirement for this type of reaction to take place, partly because I don't have the phosphonium on the other side. Another reason it's important to have an electron withdrawing group that stabilizes the carbanion is that helps the equilibrium here to favor the left side a little bit more than it would otherwise. That just helps the equilibrium have an opportunity to bounce between these two forms before the reaction kind of keeps on going. And so this principle can actually be applied to the Wittig reaction as well. So a phosphonium ylide that has additional electron withdrawing groups on it will sometimes display more E selectivity than expected. So moving away from phosphorus, you can imagine that maybe there's some reason that someone doesn't want to use a phosphonium ylide or a phosphonate ester to do their olefination. So with that problem in mind, scientists, I guess Julia and Lithgow here, they came up with a different type of olefination, and it uses a sulfone, which is this functional group right here, or I guess more specifically this functional group right here. And using this sulfone and this complicated set of reaction steps right here, you can get to E alkenes. I am going to go through the mechanism for this reaction because it ties together a bunch of different types of reaction mechanistic steps that we've talked about. And so it's kind of a nice example of just being able to tie all of that together into a what seems like very simple single process. So I'm going to pull over the first kind of half of this mechanism here. The initial step is deprotonation. So of these two hydrogens, those should be pretty acidic, pKa 31. Those get deprotonated, getting us to the carbanion. That carbanion can then do an addition to the aldehyde. That gets us to this intermediate here. And what's happening is that after this addition, the sulfur is not as reactive as phosphorus in this situation, so we don't get any of this attack over to the sulfur. Instead, we just have this intermediate, and so in step 3, what we're doing is we're adding in an electrophile to react with the alkoxide here. The usual one that's used is acetic anhydride, so I've drawn that out over here. And with acetic anhydride, we're going to get that tetrahedral intermediate formation, and then to save myself space, I'm going to combine that all into one step with the elimination. That then gets us to a product right here, which is the acetate ester of the original intermediate there. So in terms of what would happen in a lab is that I would run all of these 3 steps. So I'd have one flask, I'd add my butyl lithium, make sure I'm deprotonating everything, then I go in with a syringe and add in my aldehyde, then I wait a while for all the reaction to happen, go in and add my acetic anhydride, wait a little bit more for another reaction to happen, and then once that's done, then I would go through some processes to isolate this molecule. And so that's different from the Wittig and HWE reactions where everything happened all at once. Here I have an opportunity to purify and use this intermediate to do something else if I wanted to before I put in the alkene. When I'm ready to put in the alkene, the chemistry looks like so. So we're using a sodium-mercury amalgam, which is a mixture of metals. This is the reducing metal type of a condition, in which the sodium is kind of just transferring single electrons over to other things that are accepting electrons. In this case, what we end up getting is, overall, we're going to get that single electron transfer. Maybe I'll do that in blue here. And we do make some hydrogen radical, which we're going to ignore, but we also make sodium methoxide. And so this is a decent base, which can actually then perform an E2 reaction with acetate as a leaving group, which is a little bit unusual, but it's enabled by the sulfone here. So let me draw that out for you. If you've been paying a little bit of attention, I didn't show you any stereochemistry here, which indicates that the initial addition to the aldehyde can happen in 2 different ways, getting us to a mixture of stereoisomers here and thus here. Because of that mixture of stereoisomers here and the requirements of an E2 reaction, we're going to get a mixture of stereoisomers here, right? So the squiggly bond here indicates that I'll have some amount of E product and some amount of Z product. The magic of this reaction is that it turns out that this is also capable of accepting an electron from the sodium amalgam that's used. And so we'll get another single electron transfer process. So that gets us to that radical species now. This radical species can then fragment, getting us a kind of a leaving group here, and our alkene as a vinyl radical. So at this point, we can actually get an equilibrium. The reason being that this radical is able to kind of invert on this carbon here. So my R prime group here can equilibrate between being cis or trans to the R double prime group here. And so overall, given a little time, it'll find the trans vinyl radical form, because that is going to be a little bit more stable than the cis one. At that point, then, we would use abstraction of a molecule of methanol to get to our final product and regenerate the radical species. So again, this is a very complicated mechanism. You should get the sense that it's maybe not the most useful reaction because we're going through really strong deprotonation process. We're attacking a carbonyl. We're doing a carbonyl substitution. Then we're doing a single electron transfer, and this combination of all of these different reaction conditions may not be the best for tolerating all the sorts of different functional groups we're dealing with in complex molecules. So then, given that problem, there's an improved approach, which is to use what's called a modified Julia reaction or a Julia-Koczynski reaction. I think this is a really clever reaction. Once we go through it, you'll see how a slight modification of the sulfone from being a phenylsulfone on the previous slide to being now this heteroaryl sulfone, so some sort of heteroaromatic molecule here. That's enough to get this reaction to be simplified down into a one-step olefination. So our mechanism starts off, no surprise, deprotonation of the sulfone. Then we get the addition to the carbonyl. that point, what we've done here is now we had the problem with the Julia reaction that the alkoxide didn't really attack the sulfur in the way that we saw in the HWE reaction and the Wittig reaction. The person who figured out the modified Julia, I guess Koczynski here, what they did is to put another electrophile here. And so this is actually serving to react with the alkoxide that's formed. And so what happens is we get this attack like so. So it looks like an addition-elimination NAS mechanism. That reaction then gets us to this intermediate where we have the anion that can then eliminate to regenerate the aromaticity in this ring here. So that looks like so. And the way this happens is to actually put a lone pair on sulfur, like that, and then kick out one of the pi bonds onto the oxygen. In the product then, you're actually right where we want to be, which is to eliminate to form the double bond. And we have a case where we have kind of this gas molecule formation that's taking place, pi bond formation, that's the olefin that's being formed, and then a leaving group leaving. I should add on my T-butyl group here to get to the final product here. So something you may have noticed is I didn't address the stereochemistry that's going on as to why you get to an E alkene as the favored product. Turns out to be a little more complex than is quite so simple to get into right now. But basically the choice of the hetero-aryl group here has a significant influence because the lithium cation will actually be interacting this whole way in a way that holds everything together, that favors the formation of the intermediates that correspond to the E alkene. But for the purposes of an introductory organic class, that's something we'll just accept is the truth and not go into right now. So that was a look at olefination of carbonyls. And so you have a nice set of reactions that you can use to stitch two molecules together through a carbon-carbon double bond. The various different reactions have different purposes because you can make either the Z alkene or the E alkene. And in looking at the last two reactions here, the various Julia possibilities, these Julia reactions are really nice just because they really tie together all sorts of different mechanistic steps into an olefination process.